So I wanted to take a few minutes to show you a couple of projects that illustrate what we're talking about when we talk about high resolution drainage and how it works. Ultimately, what we're talking about is using digital topographic data from sources like LiDAR or photogrammetry or even drones to map out preferential flow paths on the surface and then be able to map the drainage catchment areas. So you may hear terms like digital terrain model, digital surface model, digital elevation model, and that's what we're looking at here. When I'm talking about these, I'm generally talking about LiDAR data, but everything that we're going to talk about today applies to drone data or photogrammetry as well. So they all start their life as very detailed point clouds. And I want to just demonstrate what we're talking about with respect to a point cloud. So as we zoom in, we're looking at all the points in the point cloud here displayed as a tin or a surface model. And if we just want to look at what the point cloud looks like, look at all the points, we can kind of see this is what we're talking about. So we've got trees, buildings, things on the ground, and the ground itself. And what we want to do is digitally bulldoze everything that's not ground off and just look at the ground. And one of the things you'll notice when we take away the non-ground points is that we do have void areas in here, and occasionally we also have little lumps and things that get left behind that are artifacts in the data that we're going to have to deal with. So the first thing that we're going to want to do with this surface is to turn it into a raster. And that means taking all these points, this is actually the representation of all the points on the ground, and taking that surface and converting it into columns and rows of pixels essentially, that or cells that we can then do really cool math with, right? We can accumulate from cell to cell, we can calculate drainage areas, and we can do all kinds of other cool stuff. And when we get an initial raw surface, right, when we run flow accumulation algorithms on it, for example, we're going to get something that looks kind of like this. So one of the first things that you'll notice is all these little red pixely dots all over the place. And these are what we call sinks, right? This is an area where on the surface model, the cell doesn't know where to go, right? There's no downstream cell from that cell, so we can't accumulate flow downhill. So it happens a lot in flat terrain, and it actually, in LiDAR data, just because of the roughness of the surface at this fine scale, we get millions and millions of these sinks. So we have to judiciously start to fill these sinks in without negatively affecting or artificially affecting the flow field. So as we do that slowly, we start to be able to accumulate flow downstream and see where the flow is going to go. Now this also assumes, of course, that we have points of interest. And in this case, we're looking at points that were provided to us by the county DPW of culverts. And so what they're interested in is looking at calculating the drainage area to each one of these culverts and seeing if the culverts are appropriately sized for the peak flows that are coming their way. And these points typically are part of a GIS system, and they include attribute tables. So here's all the attributes that come along with this set of culvert points. But really what we're interested in is some sort of a unique ID, right? This unique ID that is gonna follow us through the process, so that as we begin to calculate drainage, calculate catchment areas, and then calculate catchment characteristics associated with those drainage areas, we can tie those back to these unique IDs. So the idea is we want to use these points as the focus of our analysis, and then we start to look at slowly modifying the surface so that it drains appropriately. And once we have a good drainage surface, then we can map with very detailed precision the flow paths across that surface and the catchment areas to these points. And that's where break lines come in. So we can start to insert break lines into the point cloud to force flow where it's supposed to go, like along a roadside ditch or through a culvert. We can berm up areas to block flow or trench through areas to allow flow to continue. And that latter is the most common thing that happens, for example, at culverts. And the result is what we call a hydrologically corrected or a hydrologically conditioned surface model. It's not something that you want to use to extract elevation values or contours from, but it's been modified to support drainage modeling. So here's a couple of terms I just want to make sure we're on the same page with, right? So we have hydroflattening, which typically now is the standard for all LiDAR deliverables. We have hydroenforcement, which is really focused on streams, wherever there's actual water flowing in a stream to ensure that the water can flow downhill through bridges and culverts. And hydroconditioning, which is really what we need to do here, which deals with the entire surface. So this is kind of just a schematic example of what we're talking about. So in cross section, we have this stream, this wide stream, where hydroflattening just deals with the edges of the water. So we flatten the area where the water is. Hydroenforcement just deals with the center line where the stream is. If it's a smaller stream, just where it incisors into the landscape. And hydroconditioning is all along this landscape on either side. And it's this hydroconditioning really is what we need to be able to do drainage modeling. All right, so back to our project area, you can actually look at an example. So here's an example. Let's turn this stream layer off because it's a little bit off. We know that there's a channel running through here and it hits up against this road where there's a culvert. So when we do our original surface flow, we get something like this, where we have sinks all over the place. We're not really accumulating flow down this channel, and certainly not through the culvert because it acts as a dam or a berm where the water actually is supposed to flow underneath the road. So we start adding in some break lines, judiciously filling in these sinks, and we can demonstrate how that actually affects the surface model. So we can actually breach through here. And then when we rerun the surface model, you see that it actually performs appropriately. Now, because we're using these points, these culvert points, as the focus of our analysis, right? Once we have made some modifications to the surface model, we can run catchment area polygons and start to look at where the catchment areas are and whether or not those catchment areas are appropriate for those particular points. And that becomes the focus of our QC. So here's an area where our initial flow model, right, you can kind of see this in green, had the water flowing to the left, and after running through some iterative analysis of the drainage area boundary, we determined that the actual flow goes to the right. So this small sort of teardrop area in the center of the screen here originally flowed to the catchment on the left, and in the final analysis flows to the catchment on the right. So what we're doing is we're iteratively going around the boundary areas and looking for errors and fixing them, looking for drainage issues that need break lines, and continuing to cycle through until we get it right. So a couple key points here. It's an iterative process. You don't just queue it up, make a bunch of changes and hit the go button. You make some changes, you look at the results, you make some more changes, you look at the results, and you might run through 20 iterations or more on a surface model until you get it to perform to where you think it's performing properly. And so that brings up to the second point, and that is it's scale dependent. We're really focusing on the scale of the analysis that we need. So in our case, we have county culverts, and we're looking at the drainage areas contributing to those county culverts. As long as we've got the boundary areas right in the end, we're good. We're not so much concerned about what's going on the inside unless there's something glaringly obvious as we go through the data. And when we're done, we'll have a surface model that results in this modified or artificial hydrologically conditioned surface. And once we feel like we've got a good surface, right, then we can run it through a peak flow calculator. And what this essentially does is calculates the drainage area to each point of interest and begins to develop the catchment characteristics of each point of interest, like the average slope, the average land cover, and put those into a calculator. We can pull out the precipitation data from the web. So this is the NOAA Atlas 14 website to give us precipitation estimates so that we can run this through our peak flow calculator. And this is what the precipitation table sort of looks like when it comes out of the NOAA website. So if we zoom in on that, we can look at the frequency estimates, right? The 1, the 2, the 5, or the 10-year storm, etc. And then we can look at the duration. So for example, a 10-year, 24-hour storm would be here. So we pull this information out via the Python scripts, run it through our calculator, and we end up something like this. So here's those unique IDs I was talking about for each of the infrastructure points, right? We've got the area contributing to that, the average slope, the maximum flow length, which then goes into a travel time calculator, the average curve number, which comes from land cover and soils, and then the return interval, the 1, the 2, the 5, the 10-year return interval, etc., peak flow calculations. So one of the things that we found is that the peak flow calculations, while useful and interesting, sometimes just knowing where the water is going can be hugely helpful. So I want to shift gears a little bit here and talk about this other project. This is a project that we are actively working on with an engineering firm up in Rochester, and this is along the coast of Lake Ontario. And this is a part of the town of Greece that's been experiencing a significant amount of nuisance flooding. So if we zoom in a little bit here in an area, and I show you, we've got the stormwater infrastructure data that we got from the town DPW, and we run the surface modeling on it, and we end up with a drainage areas calculated and the flow areas calculated. And we noticed that, you know, in this area, for example, things are working pretty well, right? We've got appropriate drainage areas draining down to the catch basins into the storm sewer network. So this gives us confidence that the surface model is working well and it's paired up with the infrastructure GIS data pretty well. But as we zoom out and we pan around, we notice that there are some gaps. And so part of the process of QCing is to go through and look at why are we getting results like this. So is this, for example, a result of something in the surface model where it's affecting the flow field artificially, so we need to fix that? Or is this a function of the GIS points maybe not being in quite the right spot as far as the surface model goes, and so we can make adjustments just for flow modeling purposes to the GIS points to make sure that they're in the correct location? Even being off by 1 cell or 2 cells in the raster can significantly affect the drainage area calculations to individual points. Or is this just a function of the fact that, you know what, maybe the infrastructure is not actually capturing the drainage that it was designed to? So here's another area where we see along the shoreline, this part here in the northwest looks like the infrastructure is working pretty well. Everything seems to be flowing to catch basins and being captured in the storm sewer network. And then in this area down here, maybe not so well. So initial analysis looks like the catch basins are actually picking up drainage off the road, and most of the water that's draining in through this residential area is bypassing this storm sewer network. Here's another area where it appears that a portion of the storm sewer network is working pretty well, but then another portion in here, maybe not so much. So again, we go through this process of making sure that this is not a function of artifacts or artificial drainage in the surface model, so we try to remove those as a factor, or a function of whether the points are appropriately located, maybe making some minor adjustments in the location of the points. So what we're left with is a good functioning surface model with accurate GIS points, and that leads us to then be able to understand better what's happening on the ground. Here's another example where, in fact, the drainage looks like it's working pretty well, but we noticed some things. We noticed that a couple of these catch basins have really large drainage areas, and a couple of these other catch basins have really small drainage areas. So that tells us that it may not even be a function of pipe capacity, but just that certain inlets are getting overwhelmed. And that's an important thing to know if we're talking about retrofits and we need to either upsize or add more inlets or extend pipes, that sort of thing. So before we even go to the next step of estimating peak flows, we can use this kind of information to help us identify areas that perhaps need some additional field checking to validate the drainage and what the drainage surface is telling us, and then help prioritize what kinds of infrastructure upgrades or repairs might be necessary. So I hope this piqued your interest. If you'd like to see more, or if you want to walk through this kind of data in any sort of detail, I'd be happy to do so. My contact information is on the website, and feel free to give me a shout. And thanks for downloading the video and watching. Have a great day.